This is the presentation for chapter number 3. In this chapter, we're going to be taking a look at a composition of substances and solutions and taking a look at how to measure the masses and moles of substances and then find their concentration as molarity in solutions. So again, the objective is to calculate formula masses for covalent and ionic compounds. And then once we know how to do that, then we can define the amount or unit of mole and relate it to Avogadro's number. And then we can look at the relationship between mass and moles, and then finally we'll take a look at concentrations of solutions. So in the first chapter we talked about the micro and macroscopic. One of the ways that we measure or kind of get some insight into the macroscopic world is to take a look at the mass of things. We're going to take a look at grams. In chapter number 2, we were talking about this thing called atomic mass units or atomic mass. Remember, we were talking about the isotopes and the atomic weight, like carbon-12. Well, we can take the carbon-12, and if we divide it by 12, we end up with a mass of 1. And so on this scale, if we compare hydrogen and oxygen to 1/12 of a carbon atom, we end up with 1.00 AMU or 16.00 AMU for oxygen. So in this chapter, we're going to take a look at the mole, which is a big concept for chemistry. A mole's a unit to count numbers of particles. I mean, if you go to buy eggs, you buy them as a dozen and choose as a pair. Well, in chemistry, if we go to get atoms or molecules or ions, we usually get a mole of them. So the mole of a substance is the amount of a substance that contains as many elementary entities as there are atoms, and exactly 12 grams of carbon-12. Remember that carbon, the periodic table is based on 12 AMU. So the mole is, when figured out, is 6.022 to 1367 times 10 to the 23rd atoms in 12 grams of carbon-12. This number is also known as Avogadro's number. What you're going to find is we're pretty much going to use Avogadro's number to either 3 or 4 significant figures. So we're not going to have to worry about all these extra digits that you see on this value on this slide. Molar mass is the mass of 1 mole of anything in grams. Well, you just saw how big that number was on the previous slide. So in reality, the only thing that we really use the mole for measuring the mass of are atoms and ions and molecules. So 1 mole of carbon-12 atoms would have 12 grams. See how it's 12 AMU and 12 grams? The nice thing about this is the atomic masses that are listed on your periodic table are the same thing as the mass of 1 mole of the substance. Chemists got smart and decided that they were going to use the exact same number. The only thing that's going to get ugly is Avogadro's number, that's 6.022 times 10 to the 23rd. So for any element, the atomic mass is equal to the molar mass in grams. So if we go to find molar mass, remember the molar mass is the mass of 1 mole of something, and so we need to turn this into a conversion factor so we can do some conversions with it, similar to we were doing metric conversions in chapter number 1. So the conversion factor for molar mass is grams per mole. Now we know that there are 1,000 grams in a kilogram and 2.54 centimeters in an inch. Well, molar mass doesn't always have the same number. It all depends on which atoms and which compound and which molecule and which ions you're talking about. So that asterisk that you see means that it's not going to be in the problem. It's most likely going to be found on the periodic table. So you're going to use those masses that are found underneath the symbols on your periodic table. Avogadro's number does stay the same, and pretty much we're going to use 6.02 times 10 to the 23rd. Sometimes we'll take it out to 4 significant figures, but usually 3 significant figures will suffice for this class. How you'll have a clue that we're going to have to use Avogadro's number is it'll have this times 10 to the XX, and that 10 to the XX is 10 to the 23rd, 10 to the negative 23rd, 10 to the 21st, 10 to the negative 22nd. It'll have a huge exponent or extremely small exponent on the 10. And you'll see the word atoms, molecules, formula units in the problem. So in this problem, it says find the mass of 0.89 moles of calcium. Well, if you remember when we did conversions back in chapter number 1, if you're not sure what to do with the problem, you find the units and what it or the number and the units. And so we got 0.89 moles of calcium. Well, we don't want moles of calcium, we want mass of calcium. And we're going to use the convenient unit of grams, not the SI unit of kilograms. So we're going to do a multiplication sign division bar. And we want to get rid of moles. And we want to find grams. So we get rid of the moles. We put grams on the top. Well, remember there was an asterisk in front of the grams in our molar mass, which means we're going to have to go find some sort of mass from the periodic table. Well, in this case, it's calcium. And if you look on your periodic table and you find calcium in the second column, atomic number 20 underneath of it, it's got 40.08. So in order to find the answer to this problem, all we're going to do is, because the 40 is on the top, we're just going to multiply the two of these. And we end up with 36 grams of calcium. And you ask me, well, why is it only 36? Remember significant figures. We only have two significant figures in the 0.89. Remember, preceding zeros are not significant. So we have 36 grams as our final answer. If we start out with 1.65 times 10 to the 23rd atoms, we've got two clues of what we need to use to solve this one. Again, write down the number and what it represents. Multiplication sign division bar. If you'll notice, it's got that big huge times 10 to the 23rd, which is a pretty good clue that we're going to have to use Avogadro's number. The other clue is that word atoms. And so we end up with 6.02 times 10 to the 23rd underneath of moles. The convenient thing about this problem is the 10 to the 23rds will cancel each other out. And so this would just be 1.65 divided by 6.02. And we now have moles, but if you'll notice, we're looking for grams of zinc. So that's why I've added another multiplication sign division bar. So let's get rid of moles. Going to put zinc on the top, or the grams of zinc on top. So we're going to go to the periodic table and we're going to find zinc. Okay, and we find the molar mass of zinc. It's 65.39, and again, it's atomic number 30. And so we're going to take 1.65 divided by 6.02 times 65.39, and we end up with 17.9 grams of zinc. Remember, the numbers before the multiplication sign in scientific notation are significant. The 1.65 has three significant figures, so does the 6.02, and so we end up with 17.9 grams of zinc. So we want to know, what is the mass of one hydrogen atom? Well, like I said, if you don't know what to do in chemistry, find the number of what it represents. So we've got one hydrogen atom. So that should be a clue that we need to use Avogadro's number. Multiplication sign, division bar. Put Avogadro's number on the bottom. Notice the atoms will cancel out. And we need to divide by 6.02 times 10 to the 23rd. The issue that we're going to run into with the 6.02 times 10 to the 23rd is putting scientific notation in your calculator. Please be careful and go back and take a look at the directions of the notation that's used in your calculator. Most calculators will have an EXP button near the bottom of the keyboard, or if you're using a TI series calculator, you'll have an EE button. And if it's an 82 or higher TI series calculator, it'll be second comma, which is just above the 7 button. So this would be 1 divided by 6.02 EXP23, or 1 divided by 6.02 second comma on a TI series calculator, or EE23. And if you'll notice, that would give us the moles, but we want what is the mass of one hydrogen atom. So we're going to put the moles on the bottom. We're going to multiply by the mass of hydrogen, and hydrogen's got an atomic number of 1, and we're going to just use 3 significant figures, so 1.01. And so we get that 1 divided by 6.02 times 10 to the 23rd times 1.01. And we end up with 1.66 times 10 to the minus 24th grams. Please stop and go back and make sure that's what you're getting in your calculator. If not, then either look up the documentation for your calculator, or you can email your instructor to figure out how to get this into your calculator. So now we've got 27.6 grams of argon, and we want to know the number of atoms of argon. So I don't know what to do. I'm going to just write down 27.6 grams of argon. I'm going to put grams in the bottom, put moles in the top, because grams and moles go together, our molar mass. And I end up at 39.95 from argon. Argon's in that last column, atomic number 18. And I want to know the number of atoms, so I need to use Avogadro's number. So I'll get the moles to cancel out, and I'll use 6.02 times 10 to the 23rd, because I only have 3 significant figures in the 27.6. And I end up with 4.16 times 10 to the 23rd atoms of argon. Again, please make sure you're getting the same number in your calculator that I'm getting. So masses of formulas, or molecular weight, is just the sum of the atomic masses in AMU in a molecule. But remember, the numerical value of AMU is the same as the numerical value for grams per mole. So we've got SO2, and if you'll notice, we just add the mass of one S and two O's, and we end up with 64.07 AMUs as the molecular mass. If we want the molar mass, we just use grams instead of AMU, and it's grams per mole for molar mass. So 1 mole of SO2 has 64.07 grams. Formula mass is the sum of the atomic masses in an ionic compound. So formula mass, molecular mass, molar mass, they're all pretty much the same process. You're just adding up the mass of all the different atoms that are found in the formula. Notice this is sodium chloride, so we're going to add up 1 sodium, 1 chlorine. So now we're going to find the molar mass of KCl. So we just go to the periodic table and we find potassium and chlorine, find their molar masses. Potassium's 39.10 grams per mole. Chlorine is 35.45. And to find the molar mass, we just add these two together, and we end up with 74.55 grams per mole. Get into the habit of just taking all your molar masses out to 2 decimal places. It'll keep you from getting confused with numbers that are close to each other or odd ratios when we do some problems a little bit later on in this chapter and the next chapter. The molar mass of sodium hydroxide, we just have 3 elements to add together. So we have an Na, an O, and an H. So sodium is 22.99, oxygen 16.00, hydrogen is 1.01. We add them all together, and we end up with 40.00 grams per mole. A nice even number, one that's really easy to work with in problems. If we want to find the molar mass of calcium hydroxide, notice we've got some parentheses in this, and when we crisscrossed, we took the polyatomic ions and we put the number on the outside of the parentheses. Well, now what we're going to do is when we're going to do molar masses, we're going to deconstruct this. So I've got 1 calcium, and I've got 2 oxygens, and I've got 2 hydrogens. So if you notice, I just distributed across the parentheses. And then I find the mass of 1 calcium. Oxygen 16 on the periodic table, but I'm going to multiply it by 2 because I want 2 oxygens. And that's going to save us from having to write out all these multiplication signs times whole numbers, similar to what you saw a couple slides ago. Hydrogen is 1.01, but we need 2 of them. So we end up at 2.02. And now all we do is just add the 3 of them together, and we end up at 74.10 grams per mole. So now it says calculate the number of moles of calcium carbonate in a stick of chalk containing 14.8 grams of calcium carbonate. This is similar to those grams to moles conversions we were doing just a couple slides ago, but now we're going to do it for a whole compound. So the first thing we need to do is we need to find the molar mass of calcium carbonate. So we're going to take calcium, carbon, and 3 oxygens. So oxygen 16 times 3 is 48. And so we end up with 100.09 grams per mole for the calcium carbonate. We started out with 18 grams of calcium carbonate. See, this is very similar to what we were doing just a couple slides ago, except instead of with a single element, we use a group of elements in a compound. And we should end up with the grams canceling out, and we should end up with 0.148 moles of calcium carbonate. Again, 3 significant figures because of the 14.8. In number 3, we're going to calculate the molecular or formula mass of each of the following. So we want the mass of the whole compound. Well, P4, similar to what we were just doing, there are 4 P's in the molar mass, or the formula mass of P is 30.97. So we end up with 123.8 AMU. That could also be 123.88 grams per mole if we wanted molar mass. Calcium nitrate, if you'll notice, we've got to distribute across the parentheses, so that's where I'm getting 2 nitrogens and 6 oxygens. 6 times 16 is 96. Nitrogen's 14.01, so 2 times the 14.01. So we end up with 136.03 AMU, or we could just as easily say 136.03 grams per mole, because we do the process the exact same thing for molar mass as we do for molecular or formula mass. So it says compare 1 mole of hydrogen, 1 mole of oxygen, and 1 mole of fluorine. Which is the largest number of molecules? Well, all 3 have the same number of molecules. Since a mole is defined as a specific number of particles, specifically 6.022 times 10 to the 23rd, the one with the greatest mass would be F2, has the largest molar mass. It's got a mass of 19, so 2 times 19 would be 38. Oxygen would be 16, so it would be 32, and hydrogen would be about 2. So let's take a look at question number 9. It says, which contains the greatest mass of oxygen? Well, it would be the one that has the greatest moles of oxygen, because once you find the moles, we'd multiply that by 16. The ethanol has 0.75 moles of 1 oxygen. That's what that O means. We got 0.75 moles of O. The formic acid would be 0.60 moles of O2, because there's that subscript of 2, so we end up with 1.20 moles of O. This is kind of like distributing across the parentheses. Or the 1 mole of water. Well, water only's got 1 oxygen in it, so 1 times 1 is 1. And so what you'll notice is the one that has the greatest number of moles, because then you would just take all these and multiply them by 16.00. And we end up with formic acid has the greatest moles of oxygen. In number 16, it says determine the number of moles of compound and the number of moles of each type of atom in each of the following. So we were just taking a look at how to add the molar masses together. Carbon's 12.01 times 3, 36.03, plus 6 hydrogens, and we end up with 42.09 grams per mole. So there's our molar mass. And if I've got 25 grams of C3H6, I get rid of the grams by putting the 42.09 on the bottom. and I end up with 0.594 moles of C3H6. Okay, so that's the moles of the whole compound. So if I want to find the moles of carbon, I'm going to take, there are 3 carbons in the C3H6, that conversion factor I've created. We're going to see a couple more of those when we go to balanced chemical equations in the next chapter. And then if you notice, we've got 6 hydrogens, so I take the 0.594 multiplied times 6, and I end up with 3.56 moles of hydrogen. So if you notice, you find the moles of the whole compound, and then you can find the moles of the individual elements. Okay, so let's take a look at a couple kind of simpler problems, more of which you're going to kind of run into over and over and over again in chemistry. We want to know the mass of 0.0146 moles of KOH, or potassium hydroxide. So I'm going to add up the molar mass of potassium hydroxide. If you notice, this has been done for you in your slot notes, because I figure by now you can probably find the elements and add them together. And we want to find the mass of this mole, so all we're going to do is put moles on the bottom to get the moles to cancel out, and so this becomes a multiplication problem, and we end up with 0.919 grams of KOH, or potassium hydroxide. Number 18, we're going to kind of go in reverse, because we want to go from grams to moles instead of moles to grams. So I'm going to add the KBr together. Again, like I said, it's already done on your slot notes for you. And so I'm going to take 2.12 grams of KBr. I'm going to put the grams on the bottom. Notice that the 118 goes next to the grams. So because the number's in the bottom, this is a division problem. And 2.12 divided by 118.20 equals 0.00179 moles of KBr. And then if we want each atom, we've got 1K, 1B, and 1Br, so our number is going to stay the same for both, or 0.0179. So this says determine the mass of the following, and we want the mass of 0.5758 moles of iron 2 sulfate heptahydrate. I'm getting the hepta from that 7 on the outside of the water. And so the mass of this is 1 iron, 1 sulfur, should be 11 oxygens, 7 from the outside of the water plus 4 from the SO4, and 14 hydrogens. And when we add all this together, we should end up with 278.06, and this is already done on your slot notes for you. So we're going to take the 0.5758 moles, multiplication sign, division bar. We're going to put the moles on the bottom, put the grams on the top, so this is a multiplication problem. And we should end up with about 111.8 grams to 4 significant figures. So now we've got a 55 kilogram woman, about 110 pounds, and probably about 120 pounds. Has 7.5 times 10 to the minus third moles of hemoglobin. We already give you, that's a big, huge molecule. Look at that, 64,000 grams per mole in her blood. How many hemoglobin molecules is this, and what is this quantity in grams? So first of all, we've got the moles, and if we use Avogadro's number, we can find the number of molecules. And so we end up with 4.5 times 10 to the 21st. Again, put that in your calculator, make sure you're getting the same number I am. And if we want to find the mass of this, then we're just going to start out with the same number of moles, but we're going to put grams on the top, and we're going to end up with 4.8 times 10 to the second grams, which is about 480 grams, or basically a pound of hemoglobin's floating around in her bloodstream. This problem kind of shows you kind of the combination of the two different things we've been using, Avogadro's number and the molar mass conversions. So let's take a look at the Cullinan diamond. It's the world's largest natural diamond, and it weighs 3,104 carats, and each carat has a mass of 200 milligrams. So let's take that carats and let's convert it to milligrams. And because we're looking for the number of carbon atoms, we're going to need moles and Avogadro's number. So let's convert that milligrams to grams. And so we end up with a diamond that has a mass of 620.8 grams that's composed purely of carbon. We can then take that grams of carbon, divide by the molar mass of carbon. And now we've got moles, but we want to know the number of carbon atoms. So we're going to multiply by Avogadro's number. And we end up with 3.11 times 10 to the 25th carbon atoms. So now we'll take a look at section 3.2. We're going to be determining empirical molecular formulas. But before we do that, we need to take a look at percent composition of a compound. So if you notice, percent composition of an element in a compound is basically the percent of that element in the compound divided by the total mass of the compound. So if you take a look at our molecule, it's got 2 carbons, so we multiply the mass of carbon times 2 and then divide by the total mass, and we end up with 52.14% carbon. We can do the same thing with the hydrogen, multiplying the hydrogen by 6. And then the oxygen, we only have 1 of them. And so we end up with 52.14, 13.13, and 34.73% for the carbon, hydrogen, and oxygen. And if you'll notice, if we add all these together, we end up with 100%. Sometimes it may be 99.99 or 100.01 because of significant figures. But as a general rule of thumb, this will always round to 100% at least to 3 digits. So here we've got a problem. It's a sample of iron oxide. The total compound has a mass of 1.596 grams. 1.116 grams of its iron and 0.480 grams is oxygen. So we find the percentage of the this compound by 1. What we're going to do is we're going to find the mass of each of the elements and the mass of the total compound. And then if you remember, percent's always part over whole times 100. So we're going to take the mass of the iron divided by the 1.596, and we end up with 69.92% iron. And we end up with 30.1% oxygen. Notice this is the percent by mass. And we end up with 100.02%, which, like I said, it will basically, it's a general rule of thumb, will round to 100% using 3 digits. Not 3 significant digits, but 3 digits, or round to 100% to the ones place. Number 2, it says find the percentage of a compound containing. If you notice, it doesn't give us the total mass. So we need to find the mass of the iron, which is 17.6, and the mass of the sulfur, which is 10.3. If we add the 2 of them together, we end up with a total of 27.9. Percent is part over whole times 100. So we divide the iron by 27.9 and we end up with 63.1% iron. And we end up with 36.9% sulfur. We add them together. This time it actually adds up to a nice even 100%. The other way we can do this problem is if we're given a formula. So we've got the percent composition of water. So we've got hydrogen and we've got oxygen. Well, where are we going to get masses from? Well, remember we were using molar masses in the previous section. So hydrogen is 2.02, okay, 1.01 from the periodic table times 2. Oxygen is 16. So if we add up the total mass, we end up with 18.02. And now we're going to finish out the problem just like we were doing the previous 3. So 2.02 divided by 18.02 gives us 11.2% hydrogen, 88.79% oxygen, and 99.99 rounds to 100%. Notice this is the percent by mass, not by the percent of the number of atoms. Please be careful, because a trick question or a trick answer to this would say that this is 66% hydrogen. That's if you said, well, I got 2 hydrogens and 1 oxygen, and 2 divided by 3 is 66%. You need to remember, percent composition is percent by mass. So let's take a look at calculate the following four significant figures. Okay, so we want the percent composition of ammonia. So I've got nitrogen 14.01 and hydrogen's 3.03. Where did I get those numbers from? From the periodic table. Add them together, end up with 17.04. Percent is part over whole times 100. And I end up with 82.22% nitrogen and 17.78% nitrogen. This says determine the percent ammonia, or NH3, in this compound to three significant figures. So what I'm going to do is I'm going to take the ammonia, and if you'll notice it's in parentheses, and so a nitrogen and 3 hydrogens is 17.04. And so I'm going to take the percent or the mass of ammonia divided by the total compound, and I end up with 38.76% NH3. So now what we need to do is we need to transition from percent or masses into the simplest formula, also called the empirical formula. Okay, we always have the simplest formula for ionic compounds. Covalent compounds, remember, they don't always have the simplest whole number ratio, and that's why we use prefixes. Remember carbon monoxide and carbon dioxide when we were talking about molecules in the previous chapter. So the best way to show you how to do this is to do an example. So here I've got a organic compound, and it's got some carbon, some hydrogen, and some oxygen in it. And so our strategy is we're going to convert each of these to moles. We did grams to moles in the previous chapter. And then we're just going to find a ratio. And then what we're going to do is we're going to look for the simplest formula. So if we continue with our problem, carbon, hydrogen, and oxygen. Carbon's 2.61, hydrogen's 0.657, and oxygen's 1.73. And that's from the problem. You can see that in your slide notes. And we want to find the number of moles. Well, if you remember, we would take grams times moles over grams, and that would give us moles from chapter number 2. So what I'm going to do is I'm just going to take each of these values and divide by its molar mass. And if you'll notice, I end up with 3 numbers, and those are the moles. And now what I need to do is I need to come up with a mole ratio, or take the ratio between these numbers. This is where most students come up short on the problem, is they stop here and then do weird stuff with it. What we need to do is we need to find the simplest whole number ratio. Well, in order to get a whole number, you got to put a big number over a small number, not a small number over a big number. So what I'm going to do is I'm going to find the smallest and divide it into the rest. So for carbon, 0.217 divided by 0.108 becomes 2. The hydrogen, 0.650 divided by 0.108 becomes 6.01. And 0.108 divided by 0.108, because it was the smallest, becomes 1. Remember, the empirical formula is the simplest whole number ratio. So looking at this, you would probably assume that the carbon's 2, hydrogen is 6, and oxygen is 1, and you would be absolutely correct. So our empirical formula is going to be C2H6O for this compound. So let's take a look at a compound that's got potassium, chromium, and oxygen in it. We want to find the simplest formula. So if we list out our elements, we've got potassium, chromium, and oxygen. And then we're going to take each of those masses, divide by the molar mass. We end up with 0.17, 0.17, and 0.595. Now, again, we need to find the simplest whole number ratio between these. So I'm going to take the smallest and divide it into the rest. Notice 0.17 and 0.17. So we're going to get 1 for the potassium and the chromium. But when I take 0.595 divided by 0.170, I end up with a 3.50. And if I was to write this out, I would end up with KCRO 3.5. The issue we're going to run into is, one, empirical formulas have to be simplest whole number ratios. The other issue we're going to run into is I just can't take that 3.5 and round it up to 4. And the reason I can't do that is we're technically finding the whole number ratio of the total atoms, and that total is Avogadro's number, 6.02 times 10 to the 23rd. So half of that is 3.01 times 10 to the 23rd. And if I just rounded this up, I would say that 3.01 times 10 to the 23rd atoms is not significant, and we just can't do that. Now, if this was 3.1, I could round it down. If this was 3.9, I could round it up and probably get away with it. But we're just too far away to just say we're just going to simply round this. So what we need to do is we need to multiply this formula by a whole number to turn that 0.5 into a whole number. And hopefully you'd realize that if I multiply 0.5 times 2, I end up with 1. And so what I'm going to do is, like I said, I'm going to multiply that formula by 2, and I end up with K2CR2O7. If this was a 3.33, I'd multiply the whole thing by 3. If this was a 0.25, I'd multiply it by 4. If this was a 0.2, then I would round it by 5. And we'll see a couple examples a little bit later on, and I'll show you what you would do with those. So here we've got a neurotransmitter norepinephrine, and if you notice, it's got percents. It doesn't have masses in it. But remember, our percents are percent by mass. So if you'll notice, all I'm going to do is assume I have a 100-gram sample, because it really doesn't matter what size sample I use. The ratio is going to be the same. So if you'll notice, all I'm going to do with the percent is just turn it into grams. Then I'm going to divide each one by its molar mass. And then I need to find the simplest whole number ratio. So my smallest is 0.59. And so I get this interesting molecule that's empirical formula is C8H11O3N. But if you'll notice, this is asking for the molecular formula. Now, sometimes the empirical formula and molecular formulas are one and the same. Water is a perfect example of that. Its empirical formula is H2O. Its molecular formula is H2O. But we have a lot of organic compounds that the empirical formula is a simple whole number less than the molecular formula. And to find what that simple number is, or what we need to multiply this formula by to come up with the molecular formula, is we use the molar mass. So what we're going to do is we're going to add up the molar mass of this compound, which we did in chapter number 2, and I end up with 169.20. You'll notice in the problem gives us the molar mass is 169. Well, 169 and 169.20 are the same number, especially if you only use 3 significant figures. So what this tells us is the empirical formula is equal to the molecular formula, and they're both one and the same. So let's take a look. We got another organic compound, and this one's got 40% or grams of carbon, 6.6 grams of hydrogen, and 53.3 grams of oxygen. We're going to divide each one by the molar mass, and I end up with 3.33, 6.5, and 3.33. At this point, you may be able to just start looking at those numbers and kind of do the ratio in your head. This to me looks like a 1 to 2 to 1. And we end up with CH2O. So we know the empirical formula for this compound is CH2O. To see if this formula, the empirical formula, and the molecular formula are the same, I'm going to add up the mass of the empirical formula. and I end up with 30.03. If you'll notice, the 30.03 does not equal the 180, which means the molecular and the empirical formula are not one and the same. But it's easy to find the molecular formula because the difference between these two will always be a whole number ratio. Remember, to find a whole number, you take the big number divided by the small number. So 180 divided by 30.03 equals 6. So my molecular formula is 6 times bigger than the empirical formula. Now I'm going to find the empirical formula because you notice it's given us our percents. Remember, the empirical formula is the simplest whole number ratio. So to find that, of the moles, we need to use the grams. But remember, we just said, assume you got a 100-gram sample, and 15.8 grams of it would be carbon, and 84.2 grams of it would be sulfur. To find the moles, we divide by the molar mass, and we end up with 1.32 and 2.63. You could either put this in your calculator, or you might be able to just eyeball this and realize it's a 2-to-1 ratio. And so we end up with CS2 as our empirical formula. We've got a compound of carbon and hydrogen, and we want to know what the molecular formula is, and it's 78.1 is the molar mass. This is getting a little bit tricky because it's only giving us the percent carbon, but the percent carbon, the total percent should be 100%, or remember we took the percents to grams, so it should be a total of 100 grams. So 92.3 from 100 gives us 7.7, and that's where I got the mass of the hydrogen from. Divide each of these by their respective molar masses, and I end up with 7.69 and 7.6 moles of hydrogen respectively. And look at eyeballing these, you probably realize that it's a 1-to-1 ratio. But we want to know what's the molecular formula. So we're going to take this empirical formula of CH and find the mass of it. It's 13.01. And if you notice, 13.01 and 78 are not the same number. So I'm going to take the big one divided by the small one, and I end up with a ratio of, or a number of 6. So my molecular formula is C6H6, which is a compound called benzene, which is really interesting for organic chemists. 41, we're going to look at chrysotile asbestos. Okay, also can cause cancer of the lungs. And so if you'll notice, I've just taken the percents and just changed the percent sign to a gram. And then I'm going to find the number of moles of each of these elements by dividing by their molar masses. Going to find the simplest whole number ratio by finding the smallest one. So 0.769 is the smallest of the 4, and divide it by each of the rest. And if you'll notice, I got a 1.5, 1.49, which looks like a 1.5, and 4.00. So in order to find the empirical formula, I'm going to have to multiply all these by 2 to turn the 1.51 and the 1.49 into 3, or into a whole number. So I end up with an empirical formula of Mg3Si2H3O8. So I'm going to add the mass of the empirical formula together. And I end up with 259.84. But if you'll notice, the molar mass given in the problem is 520.8. So they're not the same. To find the molecular formula, it's going to be a difference of a whole number. So I'm going to take the big one divided by the small one. Or my molecular formula is going to be twice as big as my empirical formula. And I end up with Mg6Si4H6O16. Okay, section 3.3 is on molarity, But before we can talk about molarity, molarity is a measure of the concentration of a solution. So we can need to take a look at some properties of solutions. And then we'll take a look at actually calculating the molarity. And then we'll take a look at the simple calculation when we go to do dilutions. So if we take a look at solutions, a solution is a homogeneous mixture of two or more substances. They're basically two major parts: the solute, which is the amount that's found in the smallest amount, and then the solvent is the substance present in the larger amount. There's all sorts of crazy definitions for these, but I find the easiest definition is the solute is the smaller amount, the solvent is the greater amount. And what we find with solutions is when we start mixing our solutions together, some of them will conduct an electrical current, okay, which means they're an electrolyte. So if you take a look on the right-hand side, you'll see this nice brightly lit light bulb. And so that's a strong electrolyte. If you take a look at the one at the left, the light bulb isn't even starting, and that's probably just pure water. And it's a non-electrolyte. And then if you look in the middle, which is an interesting situation, which we cover a lot in Chem 112 when we talk about weak acids and weak bases, is it's neither a non-electrolyte or a strong electrolyte. It fits somewhere between the two, and we call those weak electrolytes. So basically, for a solution to conduct an electrical current, it's got to have cations and anions, so it's ionic. And they 100% dissociate or break apart. So here's sodium chloride. And if you take a look with the NaCl, that air with that water, H2O over the top means it's dissolved in the water because it's really not a reactant. And we end up with sodium chloride ions to carry the current. Okay. A weak electrolyte doesn't completely dissociate or break apart. What we have down here is acetic acid or vinegar, which means not all the hydrogens are going to pop off. If you'll notice, to show this, we use a double-headed arrow, and this is a reversible reaction, and that's a significant idea that we're going to take a look at in Chem 112. So acetic acid or vinegar is a weak electrolyte because its ionization is incomplete. And we'll take a look at that, a little bit of that here in Chem 111, but it's a big idea in Chem 112. How we measure our solutions is we use volumetric glassware, pipettes, burettes, flasks. Okay? And we also measure it at a specific temperature because the density of solutions can change. And we're going to have this thing called molality in chapter number 10 to help compensate for this change in density as the temperature changes. So molarity is basically a measure of concentration of a solution, and there's several different ways of measuring concentration, but we're going to basically take a look at molarity in this chapter. Okay? So it's the amount of solute, or it's the amount of the smaller part, divided by the amount of the bigger part. And like I said, there's a bunch of different ratios we can use. For molarity, we use moles of solute over a liter of solution. So we're going to put mass over a volume, kind of like a density. So to prepare a 1 molar solution, so we're going to use sodium chloride as an example. Okay, salt solution is prepared by weighing out 58.5 grams of sodium chloride. That's 1 mole. You add up the mass of sodium and chlorine. And then we add water to the 1 liter mark. So this is moles of solute over a total of 1 liter of solution. We don't take mass out the sodium chloride and then add it to 1 liter of water, because then your volume would actually go up a little bit. And quite curious, if you use alcohol, the volume actually goes down a little bit because of some hydrogen bonding and some other interactions that, again, we'll talk about those in more detail in chapter number 10. So let's take a look at a series of examples. And so example one, we're going to make a real sweet, sticky solution of sucrose. Okay, table sugar. 1 mole of sucrose, 342.3 grams. And what we would do is we would add that to some water and mix and keep mixing until we got to a liter of solution. Again, notice the order. We would put the solid in and then we would slowly add the water while stirring to get it to dissolve. Probably heat it up a little bit. More a little bit about that story in just a couple slides. So the molarity of this solution, we're going to take 1 mole, or 342.3 grams, over 1 liter. We would finally dilute it out. And we end up with 1.00 moles per liter, which are the units for molarity. So in example number 2, we're going to use 2 moles of a solute and we're going to dilute it up to 1 liter. So we end up with 2 moles over 1 liter, and we end up with 2.00 m. See, the issue we run into with molarity is its units are actually moles over liters, but I'm a lazy chemist and I don't want to have to write MOL over L over and over again, especially if I'm doing a bunch of solutions and I've got them in my stockroom. So I'm going to use the capital letter M, and we need to imprint into our heads that when we see M, that means moles over liters. So what is the molarity when 0.75 moles is dissolved in 2.50 liters of solution? So now we're going to have different numbers on the top and the bottom. Shouldn't be too much of an issue. Just put the numbers in your calculator, 0.75 divided by 2.50. And then remember, we're going to use the capital letter M to represent that moles over liters. Now let's change from using moles to grams because, quite frankly, I don't have any mole balances in the back of in my lab. So it says, suppose you have 58.44 grams of sodium chloride and you dissolve it in exactly 2 liters. This kind of sounds like the problem we started out with, the very first slide. So I'm going to take 58.44 grams of sodium chloride. Remember, we're going to convert from grams to moles. We divide by the molar mass. Here we did a lot of that in the previous section to come up with the mole ratios for empirical and molecular formulas. So the molar mass of sodium and chlorine is 58.44. That's showing up a lot because it's something we use a lot. I'm going to get rid of the grams to find the moles. And now I'm going to take 1 mole over the 2 liters. But remember, 1 divided by 2 is 0.5, but we're not going to use moles over liters. We're going to use that capital M. Both of these numbers have 3 significant figures, and that's why I've recorded as 0.500 M. If you notice, there's a lot going on in these problems. Nothing really hard, just a lot of little pieces to kind of keep track of and get used to. So let's take this one more step further. Worst case example, I got 25 grams of KBr dissolved in 750 milliliters, because all my glassware in the lab measures milliliters, not liters. So the first thing I'm going to do is I'm going to convert that 25 grams of KBr into moles of KBr. So potassium and bromine added together is 119.00. So I end up with 0.210 moles. But remember, molarity is moles per liter, and I'm given 750 milliliters. So I'm going to move the decimal point 3 places to the left, or I'm going to divide milliliters by 1,000, because there's 1,000 milliliters in a liter. I find it's easier just to move the decimal point 3 places to the left to make the number smaller, and 3 places to the right to make it bigger, considering most of our metric conversions are 1,000. So we end up with 0.280 capital M, which represents that moles over liters. So example number 6, I've got 2 grams of KMnO4. Here I've already given you the molecular weight, so you don't have to add it up. 100 milliliters of solution. So the first thing I'm going to do is convert that 2 grams of KMnO4 to moles of KMnO4. I'm going to divide it by the liters of solution. 100 milliliters becomes 0.100 liters, moving that decimal point 3 places to the left. And I end up with 0.127 molar KMnO4. Please be careful of decimal points and zeros. Your calculator likes to steal them from you. It's not uncommon for somebody in that top number to put in 0.127 instead of 0.0127 in their calculator. So please be careful when you got zeros, a lot of zeros in your numbers, and you got to type into your calculator. So now I want to know how many grams of KMnO4 are needed to make 500 milliliters of a 0.200 m solution. So now we're going in reverse. We were given grams and we want to know what the concentration is. Now I want to know how many grams I need to make a specific concentration of a specific solution. Well, if you remember that molarity was moles over liters, so M times V equals moles. Chalk into your head because we're going to use it several different times in Chem 111 and over and over and over again in Chem 112. If you see the variable V all by itself, its SI units for volume is liters. So we need to make sure that if we have a V all by itself, we have to use the units liters. If you can keep that straight, we can make these problems relatively simple to do. Because M times V is going to give us moles, and we're going to use that a lot, that ratio, M times V equals moles, in a number of different places throughout chemistry. Once I have moles, I now need to go from moles to grams. And so we had the 158.0 grams from the previous problem. And I end up with 15.8 grams of KMnO4. Dilution is the procedure for preparing a less concentrated solution from a more concentrated solution. So to diagram that, notice our little red spheres are getting further apart because we're adding more water to this solution. Okay, that solvent's in a greater amount, and now it's going to spread the solute further apart. And so moles of solute before dilution and moles of solute after dilution, initial and final. And we used to use MIVI equals MFVF for initial and final. The problem is if you have handwriting as bad as I do, my I's and my F's start to look like each other. So chemists got smart. Yeah, we are smart. Because we do things simple, or at least we think we do them simple. And instead of using I's and F's, we're going to use 1s and 2s. So 1's where we start, 2's where we end up. 1 comes first, 2nd comes later. Okay. Again, here's that relationship MV equals moles. The number of moles is going to stay the same. All we're doing is just spreading it further out. Because we have 2 V's in the problem, the units will cancel each other out, which is kind of nifty, in that we can use any of the units we want. If we wanted, we could do M times gallons if we wanted to, or M times milliliters. As long as the volume units are the same, we don't have to worry about using V as liters. So here's a dilution problem. We've got 53.4 milliliters of 0.150 molar solution. If I need a 0.80 molar solution, so I want to dilute this out, how many milliliters of 0.80 M can you make? So we're going to use M1V1 equals M2V2. My initial conditions are the 1.50 molar and my 53.4 milliliters. I want a 0.8 molar solution, so I just need to solve for V. So I'm going to send the 0.80 to the left-hand side. Because it's on the top on the right, it's going to go onto the bottom on the left. Multiply both sides by the inverse or the reciprocal. solve for V. So I'm going to multiply the two top numbers and then divide by the bottom number. And I end up with 100 milliliters to keep it to three significant figures. I could, but I'm lazy, I could write it as 1.00 times 10 to the second milliliters if I really wanted to conserve those significant figures. Example number 9, I've got 100 milliliters of a 2.50 molar KBr, but I want 0.550. So 2.500 times 100, that's my initial conditions. I want my final molarity to be 0.5500. I want to know what my final volume, or how far I should dilute this. So I'm going to send the 0.550 to the left by putting it on the bottom on the left. And I end up with 454.5 milliliters, which would mean I would take the solution and then dilute it up to 454.5 milliliters. And I would then have a solution with a concentration of 0.5500 molar. Okay, so this says to find the molarity of the following solution. Remember, molarity is moles of solute over liters of solution. So I'm going to put that 7.0 times 10 to the minus third moles over the 0.1000 liters. And then when I divide it out, I end up with 0.070 molars of I2. We're going to find the molarity of this HCl solution. But if you'll notice, I'm given milligrams of HCl, which means I'm going to have to convert that milligrams or grams of HCl into moles. So let's add up the molar mass of HCl. I'm going to end up with 36.46. And I got to convert the milligrams to grams before I divide by the molar mass. Notice that's moles over 36.46. And end up with 0.49 moles of HCl. Put that over the 0.075 liters, and I end up with 6.6 mole HCl solution, which is fairly concentrated for HCl. This one says, what is the mass of solute in 0.500 liters of a 0.3 molar glucose? So we're going to need M times V is going to give us moles. And once we find the moles, we can then moles times the molar mass will give us the grams. So we need to find the molar mass of glucose, which was 6 carbons, 12 hydrogens, and 6 oxygens for 180.18. M times V gives us 0.15 moles. 0.15 moles times the molar mass gives us 27 grams, and that's our final answer. It would be 27 grams of glucose. This says calculate the number of moles and the mass of solute in each of the following, similar to the problem we just did. We've got 325 milliliters of 1.8 molar FeSO4. So first, M times V is moles, and then we'll take the moles times the molar mass to give us grams. So let's find the molar mass of FeSO4. M times V, notice the 325 milliliters is turned into 0.325 liters. And I end up with 5.9 times 10 to the minus 7th moles of FeSO4. I can then take those moles and convert it to grams by just multiplying by the molar mass that we just added up, 151.92. And we end up with 9.0 times 10 to the minus 5th grams. Let's see, again, this is, what is the molarity? We're given a volume and we're given grams. So we're going to take the grams times the molar mass is going to give us the moles. And then moles over liters is going to give us the molarity. So here's our molar mass of HCl. We've seen that a couple times already. It'll probably start to become familiar to you. So I'm going to take the 0.3366 grams of HCl and convert it to moles of HCl. Got to remember to change that 35.23 milliliters into liters. Be careful, it's 0.03523, not 0.3523. Sometimes we write it down correctly and then type it incorrectly into our calculator, and you should end up with 0.2620 molar HCl solution. It says calculate the molarity of a 0.195 grams of cholesterol. That's a big molecule, isn't it? In 0.1 liters of serum. Okay, and this is the average concentration of cholesterol in your blood. And so I'm going to take the grams and convert it into moles, and then take the moles over liters. And so here's the mass of our cholesterol, taking 27 carbons and 46 hydrogens and just one oxygen. We end up with 324.27 grams per mole. So we end up with 6.01 times 10 to the minus 4th moles. Put it over a 0.1 liter solution, we end up with 0.00601 molar of the cholesterol. Let's see, there's about 1 gram of calcium. There's calcium ions in 1 liter of milk. What is the molarity of calcium in milk? Well, we got to go from grams to moles. And then we just divide it by a liter. So calcium ions have a mass of the same as the mass of a calcium element, because remember, basically our electrons don't have any mass, or they're not, I shouldn't say they don't have any mass, their mass is insignificant. So I'm going to take that 1 gram times 40.08 grams, we end up with 0.025 moles. Divided by 1 liter, and we end up with 0.025 molar calcium ion concentration in that. So now we have a dilution problem. See, it says solution can be diluted. So we're going to use N1V1 equals N2V2. And so we've got 1 liter of solution with a concentration of 0.250. We want to solve for the volume. So I'm going to send that 1 to the other side. And I end up with 250 milliliters. This is a reminder that the solution to our problems is liters, but this is asking for milliliters. Okay, we've been taking a look at molarity, and now what we're going to do is we're going to take a look at some of the other units that are used to measure solution concentration. Sometimes these are done by for convenience. Sometimes they're done by convention. They've always been done by those scientists in that format. As a general rule of thumb, chemists use molarity, but we also can use some other units, especially if we're working with biologists or we're working with physicists or we're looking in the medical lab community, because sometimes with molarity, the decimal points and the calculation of it is not the most convenient. So let's take a look at a couple of these. So one of the things we can do is we can basically define a solution by its saturation. Okay? A saturated solution basically contains all the solute that can be dissolved. It's about as concentrated as it can be at that temperature. Okay. A supersaturated solution contains more solute than it can be dissolved at the current temperature. Well, how's this done? We basically take a solvent and we heat it up and then keep adding solute to it until it becomes saturated at a higher than normal temperature. And then we let this slowly cool down. Okay, sometimes the excess will precipitate out. Okay, and if it doesn't, then it's said to be super saturated. We do this when we go to make candy. What we do is we take water and we keep adding a huge amount of sugar and we warm it up to make a supersaturated solution. And then when we cool down, it precipitates out or it turns into a basically a rock candy. That concentration, depending on how much water is left behind in it, determines how hard the candy is. So taking a closer look at that, we heat it up and excess solute is added to the solvent. Some will dissolve, and we heat it up a little bit more. And at first, the rate of this solution is large, and then as it gets closer and closer to the concentration, sometimes it'll reverse, and like we said, it'll precipitate out. As we cool it down, it can precipitate faster and faster. Okay. The interesting thing is when equilibrium is reached, the rates of the dissolution and precipitation are equal, and there's some dissolved and some undissolved solute. And this is like when you go to try and put sugar into iced tea, and you keep stirring it, and there's always a little bit of sugar at the bottom. In reality, it's dissolving, undissolving, dissolving, undissolving. And that's called dynamic equilibrium, or this whole idea of competing processes. Again, that's a huge part of Chem 112. The other thing we can take a look at is dissolving a gas into a liquid. We can take a look at Henry's law, and Henry's law says the number of moles of a gas dissolved in a liquid at a given temperature is proportional to the partial pressure or the pressure above it. So gas solubility in a liquid is directly proportional to the pressure of the gas in the atmosphere in contact with it. So in order to get CO2 to dissolve into a soda, what they do is they put it under a huge amount of pressure, and then they quickly put the cap on top of it so that that CO2 will dissolve into the soda. The other thing is they also chill it down because gases are most soluble at low temperature. Okay, solubility decreases significantly at higher temperatures. Here's the graph is showing you that solubility, and that's why you always find freshwater trout in cold water, because trout need a high amount of oxygen. You put them in warm water and they don't survive because there isn't enough oxygen dissolved in the water. So let's take a look at a couple of different types of ways of measuring concentration of solution. We have mass volume percent, the amount of solute, mass of solute in grams, over the amount of solution volume in milliliters. Similar to molarity, but a little bit different. Notice we're using mass and we're using milliliters instead of moles and liters. And then what we do is we multiply that by 100%. So we end up with what's called a weight volume percent, or percent M over V. Notice it's the lowercase m, which is representing mass. So to calculate the percent composition or percent mass of a 2 times 10 to the second 200 milliliter solution containing 20 grams of sodium chloride, it's just 20 grams over 200 milliliters. Notice we're just putting the mass over milliliters instead of putting moles over liters. And then we multiply by 100% to turn the decimals into whole numbers. And we end up with a 10% sodium chloride solution. So this one says calculate the number of grams of glucose in a 7.50 times 10 to the second milliliter 15% solution. So the 15% is equal to some number of grams of glucose over 750 milliliters times 100%. So this becomes an algebra problem. And so I'm going to solve for the X amount of glucose, or the amount of glucose, by sending the 750 milliliters to the top and the 100% to the bottom. And I end up with 113 grams of glucose. We can also have percent mass over mass, which is grams of solute over grams of solution. Typically, this is done with like amalgams, and so if you notice, we've got gold and platinum. So we want to know the percent platinum. So it's the mass of platinum over the total mass of the solution times 100%. And we end up with 24.32% platinum. Parts per thousand and parts per million. Again, sometimes the molarity is just not small enough. So if you'll notice, we use the percent and we just multiply by 10 to the third to get part per thousand, 10 to the sixth to get parts per million, 10 to the ninth to get parts per billion, 10 to the 12th to get parts per trillion. Okay. Again, they're used for very dilute solutions, and we're actually getting the technology to measure the parts per billion and maybe even the parts per trillion concentration for some molecules. So this says, what mass of solid sodium hydroxide is required to prepare 1 liter of a 10% solution of sodium hydroxide by mass? Okay, the density of the solution is 1.109 grams per milliliter. Okay. A lot going on, but let's start out with the density. We have a solution that's 1,110 grams. The mass of sodium hydroxide is a 10% solution. And so 10% of that's 111 grams, which is the sodium hydroxide. Sodium hydroxide is 97% by mass. And so we take that 111 and we end up with a total of 114 grams of sodium hydroxide we find in the solution. Okay. These can get a little bit tricky, and when you get your problem set, which you're going to find out giving you a couple hints. In Canada and the United Kingdom, devices that measure blood glucose levels provide a reading in the millimoles per liter. So we want to know what the concentration of glucose. So again, the molar mass of glucose is 180.18 grams. We've seen that. And milligrams per deciliter. A deciliter is 0.1 liters. So I'm going to take 5.3 millimoles times moles over 1,000 millimoles. So I end up with 0.0053 moles for molarity. M times V gives me 0.00053 moles of glucose. Then I'm going to take the moles times the molar mass. And then that gives me grams. So I'm going to multiply by, there are 1,000 milligrams in a gram, so I end up with 95 milligrams. And so I end up with 95 milligrams per deciliter. And for those of you who are familiar with glucose tolerance test, 95 milligrams per deciliter, or 95 on the glucose tolerance test, is basically within the normal range. Let's see, a throat spray is 1.40% by mass phenol, so I'll give you a molar mass of phenol. If the solution has a density, calculate the molarity of the solution. Well, molarity is a liter of solution. So we assume 1 liter, then that's 1,000 milliliters. We multiply it times the density of the solution, which tells us that 995.6 grams of solution. The phenol is 1.4% of that. So there should be 13.9 grams of phenol in it. Convert the grams of phenol to moles of phenol. And molarity is moles per liter. That's why we started out with 1 liter or 1,000 milliliters. And we end up with 0.148 molar C6H5OH or phenol. Number 79, IV solution, D5W, dextrose, 5%, okay, in water. It's a very common IV solution. It's 5% by mass solution of dextrose, which is D-glucose. So here's the molar mass of glucose. Here's the density. So we want the molarity. So let's start out with 1 liter, because molarity is moles per liter. And so we're going to have 1,029 grams of solution, 5% of which is dextrose. So we end up with 51.45 grams of dextrose. We got to take the grams and convert it to moles. We end up with 0.286 moles, but because we started out with a liter of solution, moles per liter, we end up with a 0.86 molar solution of dextrose.